Thank you for having me. My name is Ashok. So I'm a senior principal engineer at Oracle Cloud and presently at Oracle Health, and we are building agentic care platform framework and a couple of agentic solutions for the healthcare platform right now. But I was extensively also working in the GPU platform for orchestrating GPU workflows, and I know how do you run ML jobs, benchmarking, stuff like that. So that was primarily at Oracle. So, right, get into the scaling ML infrastructure problem, which is what you guys are here for. Thanks for coming over again. So, I would like to start with the actual bottleneck. So, the bottleneck of the problem today is actually the compute demand, right? So, everyone's just going crazy about compute. It's funny because maybe a couple of years ago, anyone wants to start a company, you want to go to a website, you just do a website, and then you build the applications, and then suddenly all of a sudden compute's just becoming the major important problem right now because you want to run ML ops and you want to run GPU flows, and people are really getting into data. There's just so much data to chunk. And then how do you run the data? How do you run process, right? So then compute becomes a problem because compute is just not something anyone can, anyone can offer. So just like big players, like really big players can offer, right? So like Google Cloud, like Oracle, AWS, Azure, like really only big players can offer, right? So this has become really a big problem. But again, there are a lot of companies right now going through this compute demand problem without even understanding what is the problem. So this talk is essentially about that. How compute demand is important, how it will help with your ML infrastructure, and how actually you can use, Airflow specifically here in this case, to enhance and scale your compute infrastructure. So getting into the problem, right? So I'm going to go in a couple of directions here. So I'm going to talk about the foundation. Then I'll really talk about the logic plane or the control plane, as people understand. Scaling the pipeline, then how Airflow fits and where it fits, then some of the key takeaways and guidelines I probably would like to explain. Again, all of this, whatever I'm just going to be proposing or suggesting here is an experiment which I have done. So it's not a representation of the whole company, just for the disclaimer. So the foundation here, the Kubernetes, which is the paved path. I think a lot of people already know about Kubernetes, how things works. But still, I think there's a nitty-gritty things about how you really run Kubernetes at scale, because it's just not easy walk. I would say it's not a piece of cake, because when you run things at really scale, for example, 125,000 GPUs running all at the same time on a Kubernetes is a overkill. Probably not everyone's facing them. That's what I've seen. And like we were running 125,000 bare metals, right? And then we see Kubernetes able to handle them. No, it throttles. So what are the learnings there? Like how you can really enhance Kubernetes from there, and where does really Airflow fits in? So it's kind of a combination of where you really want to go into this whole strategic thinking. So the build path is essentially Kubernetes. Yes, it's there, but what combination does it really work? So that's what we're going to go in. So I want to compare between like what was previously there and what's currently, again, in the paved path, which is the bare metals, right? So if someone wants to go run a GPU job, let's say like 5 years ago, they go to bare metal and basically just use a GPU, right? So, for example, I used to be in a lab like probably 10 years ago. Sounds like long back right now, but 10 years ago, where I used to like really wait for someone give me the bare metal once they finish it in my lab, because they have to finish it. Then only I can take the bare metal and use it for my jobs. And right now, that's not the case, right? So you basically just go log into any cloud provider and then say, I need a GPU, and they give you the GPU. So how do they give the GPU? Essentially through some sort of jobs, and basically they orchestrate all those jobs. And you really want to understand that. Why you want to understand that? Because it costs you so much. So you want to understand what you run so that you can actually optimize for it. So that's basically the bare metal as the paved path. And people don't understand the paved path even now, and that's why they cost a lot, because people really spend in billions of dollars right now. Small companies, like startups, are spending in millions of dollars because they don't even understand the paved path. And that's exactly why you need some sort of a real good logic control plane, which can save you that cost. Because, if you want to run jobs, you want to run it efficiently. So that logic plane is really important. So I'm going to go from again, bare metal to paved path, which is the self-service Kubernetes from cloud providers, to a logic control plane plus the self-service path. Now, again, Kubernetes for GPU abstraction, right? So like I mentioned, bare metals, again, Kubernetes is a great option in this case. There's also a lot of other industry-wide, also some proprietary softwares which Microsoft offers, as I understand. But Kubernetes has been working really well, so I would recommend definitely using Kubernetes. Also, Pulumi works if anyone has experience with Pulumi. But the resource allocation in Kubernetes is really amazing, like pod limits and requests which you can provide. Some of the decoupling you can do is amazing, and you can actually do dynamic scaling. For example, you can have workers, and you can have assistant workers, and basically a controlled worker. And you can do all of these operations right now with Kubernetes, but still there's one missing piece. Like, yes, you have control workers, there is assistant workers, which you can run GP jobs on, but there's one missing piece, which is basically how you orchestrate all these workers, the control, the assistants, all at the same time to make sure you are able to orchestrate the GPU for the right data pipeline. That is the whole big question which we are missing, because you need some sort of a logic plane and a control plane. I hope everyone understands where we're really heading towards here, right? So maximizing your GPU return on investment. I will buy GPU right now for price. Let's say I get something like an NVIDIA GB200 Blackwell chips recently, which got released, right? So let's say we go get that. They cost like $10 an hour or something. You buy them, and let's say you run your jobs. That's one GPU, by the way, right? So you need like 64 GPUs in some scenarios. And some scenarios we don't even directly use the GPUs, but you don't know that you're using GPUs because you're running your inference jobs through some other API, and those jobs are in the background is actually just a ray job, and the ray job is using the GPUs, and for which you're paying the price. So it's all intertwined, and we all need to understand this. So that's your return on investment. So you want to understand which jobs you're running and how do you maximize that. And Kubernetes, as I was explaining, is basically a good place to start. And we want to understand what all components is there in return of investment, right? So automated provisioning, dynamic right sizing of the jobs, and you want to understand like what spots are available, what GPUs are available at the right place, and you want to understand what really fails, right? So if someone's actually having their own custom models, custom configurations, where things are failing, you don't want to have a GPUs in an idle state. You don't want to have jobs in idle state. We have seen, for example, we are running like thousands of workers, thousands of jobs, and we have seen there's a 2% of the workers are failed in your Kubernetes pod, right? Like 2% of the pods failed. And then like what the cost of the 2% here? It's basically some real physical hardware in the background, and that's actually the cost you're incurring. So how are you optimizing for that? How do you ensure that 2% doesn't fail? Maybe bring it down to 1%, maybe bring it down to 0.5%. So that's your logic plane again. So that's maximizing GPU return on investment. Here comes the ML orchestration flow, right? So far we have been discussing about how you actually run GPU jobs. What is the importance of GPU's return on investment? What is the importance of really getting into, like a self-service mode where I want to run a number of data models, data pipelines, and jobs? Like, how do I really take things to production? Like, you want to take, essentially, like, what are we really trying to do, right? So you want to take a product out. Let's say it recommends something. Let's say it runs a job which tells people that, hey, you're having a good day, for example, right? Like how? By analyzing the data. So basically, you really just want to take some business solution out. Like, then you want to orchestrate it. Then you want to have a pipeline for it. Then you want to have a continuous rundown of information, which sounds like a feedback loop. So all of this needs to be there. In this case, whatever I just mentioned was done by Kubernetes in isolated modes. They all are isolated, right? Now, what we want to do is not an isolation, but as a pipeline. And that's exactly where MLOps comes into place, right? So the Airflow is basically is a good general purpose orchestrator. So what you can really do here is the MLOps has a lot of heterogeneous tasks. So the heterogeneous tasks like data modeling, compute, what kind of GPUs you need, where do you need, what batches do you need, and what models you're going to use as a model registry, and where the models are being served, how is it served as a serving layer. There's like a lot of components in this. And you just don't have like a single tool or like a single application or a server which can just support all of this, right? You need multitude of services, multitude of applications, where we need something to connect them all together and then run them in a DAG. Essentially, Airflow serves a purpose. So it's a general purpose orchestrator in this case, right? So it just glues everything together. And unfortunately, we have worked with a lot of data scientists, lead scientists, and a lot of people knows Python, and then Airflow's in Python. So it just gets easy, right? So three pillars, which I want to highlight. So you actually want to make sure you understand the data agnodism, scalable compute, reliability. So why these three things important is because when you talk about, like in this case, I want to run a GPU model, right? So I want to go train something, infer something. You are basically, you don't even know what data you're manipulating with or you are working with, right? So it could be a video, it could be an audio, it could be any type of data. So you want to understand, orchestrate this ETL of that data, right? So that is understanding any type of data formats, scaling the compute. Like I mentioned, let's say suddenly you see a spike, and then you see, okay, I have some like, let's say some 1 million users using this and inferring through this model, and suddenly it becomes a 10 million, right? Then it drops again, it becomes a 1 million. Like how do you scale for that? So you need autonomous load sharing, right? And you want something logically orchestrating that autonomous load sharing, and that is scalable compute. Reliability. So reliability is essentially making sure, when I just mentioned that you want to immediately spike up and spike down. Did I miss any request? Did I drop any network? How I'm not in a data drift mode, how I'm not in a model drift mode. If anyone understands what's a model drift here, ask me questions later if you want. But essentially, how you ensure that that's resilient. So those are all important aspects of MLOps, and Airflow actually can serve this purpose by just running these jobs as multitude of services. So a seamless integration with the compute plane, as I mentioned. So you can basically just have Airflow as your commander in this case, which is you run, you have your DAG mentioned, determined with exactly predetermined steps of what you want to do, what Kubernetes, what rules you want to write. You can actually have your workflows as a task flow, and then you just isolate your tasks. Each task serves a different purpose, like data modeling, resource pipeline, and Airflow basically works as a commander in this case. So orchestrating the data pipeline. So I would like to understand, I would like to go into like specific things of like what you really, how you want to really do this, right? So in this case, as I mentioned, data orchestration is an important thing. Compute is another thing. Reliability, security, availability is another important aspect, right? So with the data dependencies, what are the important things you want to actually, target with Airflow? So it really works well for ingesting, validation, feature engineering, and the feature store load. With the existing things which already Airflow offers. For example, I'll get into the XCOM, for example, where you can share parameters, right, in the next few slides, and obviously the task flow where you can actually register the tasks. So there are really good data dependency workflows which you can run. And you can also mention different types of DAG on a different basis. For example, different use cases might want to have different types of DAGs. Different data pipelines might want to have different types of DAGs. So you actually can also do that. So these are all real good flexibilities in kind of a data preparation where Airflow supports. So continuous training, right? So with any MLOps, again, as the saying goes, don't just rely, I don't know if it's a new saying, but don't rely on LLMs for all your answers, right? You want to have a combination of solution. So that's a different talk, but again, the continuous training is important. Say for your combinations of solutions, continuous feedback loop is important. So essentially, event-driven scheduling, continuous model registry, new different types of versions coming into place. For example, I have model A, model B. Whatever version works for you. Who decides that? Something needs to decide that. Essentially, that DAG which you did in your data preparation and in your continuous training, Airflow decides that. So these are all rules-based DAGs you can actually work through in Airflow. Now, logic versus control plane. How do you combine these things? I just mentioned, okay, you can run you can run a logic. You have the Kubernetes. On paper, theoretically, it makes sense. Okay, you have this whole thing connected together, and then you can run them. But there's a major problem here, right? Because we shouldn't really confuse your VCNs and connectivity, networking, provisioning with with your Airflow or Kubernetes pod, and that's a completely different layer. So you want to actually put them in different layers. So your physical layer, your provisioning of your compute bare metal is a different layer altogether. So let's not confuse that. So Kubernetes is actually running on your top, which is basically just provided on top as a Kubernetes service where you run your GPU jobs. So those are just plain jobs, and you basically have a control plane logic as Airflow underneath. So Airflow and your GPU jobs on top run through Kubernetes. So that's how simply you can do it. A lot of people confuse this with like my entire end-to-end solution I'm going to do with Kubernetes and Airflow and Kubernetes again. That's not going to work. It doesn't scale well that way. You want to still go with Terraform. You want to still go with a really good solution for your IAC where infrastructure as code works. So that's kind of what the best solution is. But most cloud providers actually have a good pattern for this. If you don't use a cloud provider, you are using self-hosting, you actually can just follow those patterns. But on top of that, you actually want to do the the actual Airflow as a logic plane, and then running your jobs only for the GPU and data pipeline. Do not basically mix and match with your provisioning of your actual systems. That doesn't really work well. So scaling compute and data with Airflow. So far we discussed about like how do you do data preparation pipeline, what can you really do, how you can really do, right? So now comes the scaling problem, because let's say you do it, you go ahead and then start doing the data preparation, and suddenly you start seeing petabytes of data coming through, right? So there's too much data inflow. How do you start to manage that? How do you train? How do you experiment quickly, right? So you want to have like, for example, in this case, I'm just providing like a need where I have 50 different types of data sets, and then I want to go do a hyperparameter transformation, and then do my model training, inference training again. How do I do it? So there's basically this. You have this dynamically allocated tasks which you can use. So there are a lot of flexibilities where you can just dynamically allocate tasks, dynamically provide numbers, and also tweak those in the through the K8s executor, because you can say, hey, take this parameter and run this job where you're going to run this with 4 GPUs, and then take this parameter and kill that 4 GPUs and run again with 2 GPUs. So you can basically just mention different types of things here. And that's very flexible, and I like that, because earlier I used to do this manually. So that's just fun. So again, data sharing. So when I just said that you can actually run through multiple different parameters and hyperparameterization, you can actually also, one thing you want to do is share data, right? So for example, I run 4 different jobs, and then I get a result. Obviously, you can store the result, and but again, storing the result, putting it into a vector space, getting that back again into a new data store, again pulling it for the job, just not going to work in real time. It's pretty slow. So you want to just share the hyperparameters, right? So the way you can just quickly share is through XCOM. So you just basically it's just flexible. So these are a couple of small tweaks and quirks I like. And again, obviously the task flow API and the Pythonic ML, right? So you have the task flow, which actually through which you can provide your dynamic tasks and generate dynamic tasks and just register through it. So what I just mentioned with this, you're running through multiple different jobs, and 2 jobs versus 4 jobs versus 8 jobs. What do you want to run? You can dynamically register them, and how you register them through the task flow API. And obviously, you have Pythonic ML, which gives you like a much better support of ML developer experience. So where you can basically just add a lot of different Python libraries for ML data preparation and model training, which is already readily available, and it's just compatible for you, right? So this is a really important point, because when you're really setting up your system and you see a bunch of package errors, you see a bunch of issues where I'm not able to integrate with PyTorch, I'm not able to integrate with some other platform, like let's say Google Office or someone else's Office. It's just going to be really hard to integrate in that case, because you're going to work with data scientists, not just software engineers. So everyone needs to be comfortable doing that, and basically Pythonic ML comes to the save and helps you with integrating with different platforms much easier. So this combination of Airflow where you can do the task flow API and provide different data jobs, and data jobs having Pythonic ML integration where different developers or data scientists can work, just gives you a good environment essentially. So another important thing of the infrastructure setup, again, infra in this case is not VCN, not networking, is essentially creating your actual layer of running those jobs, right? So when I just mentioned I want to go, let's say I can take a use case, right? I have not just explicitly mentioned because I don't want people to read the example. So essentially, let's say you just decided that I want to. I'm running through a help assistant, and the help assistant asks me for, can you tell me if this router connects to this, and give me some technical information, right? So immediately what you can do is you can spin up a job and ask the relevant model, and then get that information and give that information back to the help assistant. So this you can do through like integrated agentic workflows. And these agentic workflows, as you integrate, you had to go run the model. How did you run the model? You basically need to set up your infra immediately, right? You need to run an immediate job there. And that's exactly what this Airflow can do, right? So you basically just go trigger the Kubernetes to ask for like, hey, run this job. I want to run this immediately and then get this result back. And that just set up your new infra for you, where you can run the job on an entirely new GPU or entirely new system, which auto scaled for you for a different purpose, which didn't even exist before. And you can also tear it down because you just don't need it anymore. So because you just ran that exactly for that job. So you can just quickly spin up something, quickly bring down something. These are all something we experimented. Again, I'm not saying that these are in practice, but these are experimented and probably good techniques to use. So what's beyond, right? So there's a lot of good capabilities I mentioned. There's also a lot of things which actually, not really good experience. For example, I would, as I mentioned that for the infrastructure teardown, and like you essentially just want to use a really good infra code. The problem of connecting the logic code with the infra code is really tricky and really difficult. So we really need experts for that. So people who really understands, underlying Terraform or underlying CDK, like they're just people who understands them really well. And I think those are really good experts who can actually, connect these dots really well together. And again, with more native support, with more evolving things, and I just feel maybe there is a problem where you might not be able to keep things up to date. So you really want to have like a more hybrid solution. Yes, Airflow is good. You can have a logical control plane, but do not take tighter dependencies where you are not able to integrate your jobs with different types of platforms or different types of Pythonic or different types of ML libraries for that matter. Right? Make sure that you're only keeping it for the logic flow, and then have your tasks hybrid, isolated, heterogeneous, so that Airflow doesn't, become a bottleneck for you. Finally, for production, and a couple of things I just want to quickly mention is there is, like I mentioned, there is so far whatever you just build, you want to take it to production, right? So CI/CD is pretty important, and you want to have continuous training, continuous deployment. So what I just mentioned exactly here, with an infrastructure as a code capability, can be immediately turned into a continuous integration platform and development platform where you can you can continue to develop, continue to deploy, and that's just feasible with this. And obviously, best practices for modular DAGs, and you don't want to have multiple or like a big, huge DAGs with one single thing, and everyone's updating the same thing over and over again. That's just going to cause chaos. Security is actually an important thing here, again, because you're going to go, let's say, with the logical flow, and you want to bring up GPUs and bring down GPUs, or bring up multiple jobs and bring down multiple jobs. Security is really, really critical. Otherwise, you're going to burn anything, possibly. So do not hard code information, right? And do not write any secrets directly there, and don't give any information which you are might be having to go give to some other external entity, right? Like you might have to, let's say, connect to a third-party vendor to run something, and your Airflow is executing that, or your DAG is executing that. So you want to make sure that you don't provide that information outside. So yeah, reliability is very, very important. So this actually gives you logging metrics, and also Airflow gives you a UI where you can all handle that. So that's an amazing feature. So one final thing, and then I'll quickly finish. One thing is that human factor. So just like that I mentioned, like there is a lot of automation you can do, a lot of logical flow you can run. You can really enhance the infra, but the human factor of having to make sure that someone checks it is really important. Every time you do something, you know that this flow is actually gonna break or make or break things. So you want to make sure that the human factor is involved and ensure people are reviewing it. So yeah, final thing is basically, I just mentioned about Kubernetes executor. How do you do dynamic task mapping with Airflow and XCOM for metadata hyperparameterization? These are important 3 things I mentioned as maybe a suggestion. People can actually utilize that. So yep, pretty much that's what it concludes my presentation. And you can use the logic, Airflow as a logic orchestrator and get your maximum return on investment for the GPUs. Thank you.